Okay, so this lesson is for Mrs. Cucci's College Now Pre-Calculus class. You should be on file 3.2, Graphing Polynomial Functions. So please have that open in front of you. Okay, so by the end of this lesson, you should be able to, graph polynomial functions and use the intermediate value theorem to determine whether a function has a real zero between two given real numbers. Okay, so in addition to using the leading term and finding zeros of a function, it's helpful to consider the following facts when graphing a polynomial function. We're going to do a lot of graphing with polynomial functions, so this is going to be very important. If some polynomial function p of x it has a degree of n, then the graph of the function has at most n real zeros. So if the highest exponent of the degree is 3, then you should have at most 3 solutions, or 3 zeros. And at most n x-intercepts. Sorry, that's supposed to say most, not mo's. You should also have at most n minus 1 turning points, so maxes and mins. Turning points are in a graph we, like I said, refer to relative maxima, relative minima. Those occur when the function changes from decreasing to increasing or vice versa. Okay, so we're going to graph the function h of x equals negative 2x to the fourth plus 3x cubed. We're going to use graph paper, and we're going to use the skills that we've learned. So you're not going to be doing this on the calculator. You're actually going to be using graph paper, so make sure you have that out in front of you. Okay, so we have the function f of x equals negative 2x to the fourth plus 3x cubed. And we want to graph this. Okay? So what we're going to do is we're going to first use the leading term test to determine the end behavior of the graph. Our leading term we know is negative 2/4, or negative 2x to the fourth. Sorry about that. Okay. So the degree of this polynomial is 4. Okay. We know that 4 is even. And the coefficient is negative 2. Okay. And then we're dealing with negative. So we're dealing with even degree, negative coefficient. So our end behavior should be as x approaches infinity and as x approaches negative infinity, we're going to be decreasing. So it can be sketched like this. We don't have to get fancy. I'm just asking for a sketch. Okay? So I know because of my leading term test, because my degree is even and my coefficient is negative, the end behavior as x approaches negative infinity is going to be decreasing, and as it approaches negative infinity, it's also going to be decreasing. Okay? Okay, so that's just a little bit of the information. So next thing we want to look at is what our zeros are going to be. Okay, so what our zeros are going to be.
Move over eBay. There's a new auction in town, and it only takes a penny to get in on the action.
Dorothy Tucker takes a look at penny auctions, which can be a bargain.
Okay, so next thing we want to look at is the zeros of the function. Okay, and we can very easily find the zeros by taking my function and setting it equal to 0. Okay, and then solving for that value of x. So we know that we can pull out a GCF, negative x cubed, which is going to leave us with 2x minus 3 equals 0. Okay. And then zero product rule tells me I can take each one, set that equal to 0. And we're going to get x equals 0 and x equals 3/2. Okay. So now we know what our zeros are, and we can go ahead and put those on the graph. I know I have x equals 0 and 3/2, which is 0.5. Okay. So we've got a bunch of information here now, but not enough. Because this was a cubic, we can say that 0 has a multiplicity Yuck. Does not look nice, does it? So 0 has a multiplicity of 3. Reason being is when I take the cube root, I wind up with 3 roots there. So 0 has a multiplicity of 3. 3/2 has a multiplicity of 1. Okay, because it's only occurring once. The degree on that x is 1. Okay? So we do have those x-intercepts of 0, 0, and 3/2, 0. So what we need to do now is we need to take those zeros and we need to divide that x-axis into 3 intervals. Okay, so those intervals are going to be from negative infinity to 0, and from 0 to 3/2, and again from 3/2 to infinity. Okay, so we've broken it up into 3 sections. Okay, so what we're going to do is we're going to figure out about where those values are, the sign in between them, if we're dealing with positives or negatives. So what we're going to be dealing with is some test values. Okay, so what we're going to do is we're going to make a little table. We've got my interval. Okay, so we're dealing negative infinity to 0 for one interval, 0 to 3/2, and 3/2 to infinity. Okay, we're going to do a test value. So the test value we're going to use is going to be within that interval. So let's say negative 1, 1, and 2. Okay. The function value. Okay, so when I plug it into my polynomial, what do I get? And then location on graph. Okay, so that function value, when I take my negative 1 and I plug that into my function, and again, my function is negative 2x to the 4th plus 3x cubed. If I take that negative 1 and I plug it in, I get negative 5. If I take the 1 and plug it in, I get a 1. If I take the 2 and plug it in, I get a negative 8. So these become points on my graph. So this allows me to figure out where things are going to be placed. This is going to be below the x-axis. Okay, negative 1, negative 5 is below the x-axis. This is going to be above, and this is going to be below. So that gives us an idea of how this graph is going to kind of be set up. Okay, another way to look at it, and generally we're going to be setting things up a lot of times like this. So it's important that you see this. Everything from here we're going to be negative we're going to be positive in between my 2, and then beyond this we're going to go back to negative. So above and below that x-axis. Okay, so we have our test points. We've done all of that. The next thing we need to deal with is, and this is step 4, this was step 3, is dealing with finding the y-intercept. So I know that these are long, but you do have to know how to do these out. Okay, so to determine the y-intercept, all we have to do is, if we have my function h of x, we have to find h of 0. Okay, y-intercept, you plug in 0 for x, x-intercept, you plug in 0 for y. So we get negative 2 times 0 to the 4th plus 3 times 0 cubed, and we wind up with 0. Okay, so my y-intercept is the point 0, 0. Okay, so we have found a whole bunch of information already. We know we have my y-intercept 0, 0. We have some points from up here that we found. We found the point negative 1, negative 5. We found the point 1, 1. We found the point 2, negative 8. We found my x-intercepts to be 0, 0, and 3 halves 0. So we have a whole bunch of points that we can now work with here. Okay. Okay, so what we're going to do is we're going to use that information to help us build a graph. Okay, so I've got my x and y axis, and I'm going to make it like this, because originally when we went and sketched the graph, we said it was going to be decreasing as x approaches infinity and decreasing as x approaches negative infinity. So I know that my end behavior is going to be going down towards negative infinity. So chances are I'm going to want my x-axis lifted. Okay, so the next thing I'm going to do is I'm just going to real quick throw in some values. Why are we disappearing on me? Some values here. It's tricky. Okay, so we're going to put in my points that I have. We had my zeros at 0, 0, and 3 halves 0. 3 halves is about 1 1/2. Is exactly 1 1/2. We had the point 1, 1. We had the point negative 1, negative 5. We had the point 2, 8. Okay. So what we're going to do from there is we're going to think about how this worked for us, okay? Remembering my intervals here. I am below the x-axis from 0 to negative infinity. So I know that this is going to be going down, okay? I'm above the x-axis from 0 to 3 halves, okay? So this is going to be coming up, and then we are again below the x-axis from 3 halves to infinity. So we wind up getting this kind of looking graph. And because we know it's x to the 4th, we know that the general form does kind of look like something like this, maybe a little less pronounced. So that would make sense. And again, my end behavior as x approaches infinity is descending or decreasing, and as x approaches infinity is also, okay? So that's how we are able to sketch the graph. So the last thing we want to do is we want to label it. H of x equals negative 2x a to the 4th plus 3x cubed. Okay? And we're going to do quite a few of these for practice. Okay. So, the steps that you take when doing this is you're going to graph these polynomial functions. First thing you're going to do is you're going to use that leading term test to determine your end behavior, which is the first thing we did. We decided that as x approaches infinity, it was decreasing, and as x approaches negative infinity, it was also decreasing. The next thing you're going to do is find your zeros by solving for f of x equals 0, so setting the function equal to 0 and solving out. So that finds your x-intercepts. We're going to use those x-intercepts to divide that x-axis into intervals, And we're going to choose a test point in each interval to determine the sign of the function value. So determining if it's above or below that x-axis. Then we're going to find f of 0, which gives us the x-intercept. And if necessary, find any additional values to determine the general shape of the graph. And then we're going to draw the graph itself. As a partial check, you can use your calculator to plug that in and see what it looks like. But you do have to be able to do them out by hand. Okay, so we're going to try this one. 2x cubed plus x squared minus 8x minus 4. Okay? Okay, so we have our function here. We've got f of x equals 2x cubed plus x squared minus 8x minus 4. Okay? So we're going to go through the steps and we're going to figure out how to graph this. So step 1 is to determine that end behavior, right? Leading term. Okay, my leading term I know is 2x cubed. Okay? The degree is 3. So that's odd, right? Degree is 3 is odd, and the coefficient, I should have an e in there, sorry about that. The coefficient is 2, which is positive. Okay? So my degree is 2, and my coefficient is positive. So my end behavior is going to kind of go something like this, right? As x approaches negative infinity, I'm decreasing. As it approaches positive, I'm increasing. Now, is this going to be the general shape? Not necessarily, but it just gives us an idea for our end behavior, that's all. Okay? So step 2 is to find the zeros. So we have to take my function and find f of x equals 0. Okay? So we're going to take my function and set it equal to 0. Okay? And the way that we solve this is we're going to have to use my factor by grouping, and we've done this many, many times now. GCF in the first half is x squared. So we're going to get 2x plus 1. And in the second half, I'm going to pull out a negative 4, and we're also going to have 2x plus 1, which gives us x squared minus 4, 2x plus 1, x plus 2, x minus 2, 2x plus 1 equals 0. Which is going to give me values of x equals negative 2, x equals positive 2, and x equals negative 1/2. Okay? So that gives me each having a multiplicity of 1. Okay? So those are my x-intercepts, negative 2, 0, 2, 0, and negative 1/2, 0. Okay, so what this does for us is it winds up breaking. Okay, so what we're able to do with these zeros is break them up into intervals. Alright, so we're going to take these and we're looking on the interval from negative infinity to negative 2, negative 2 to negative 1/2, negative 1/2 to 2, and then to infinity. And we're going to break that apart so that we can figure out if we're increasing, decreasing, above or below the x-axis using the table that we built before. Okay, so building that table. Got your interval.
runs out of the house to get away from this. Because you escape. You move this right, Mrs. Smith.
Okay. You have your test value. I'm going to call it TV for short. We have our function value. So when you plug it in, what you get. Okay. And then the sign. And location of the graph. Okay. So my test value, we're going to pick some nice easy values. Let's choose -3, -1, 1 and 0. I'm sorry, 1 and 3. Okay. And now we choose our function value. So when we plug this into the function, we have -25, 3, -9, and 35. Okay, so I am a minute over my time here, so I'm going to come back to this and we're going to finish this in the next lesson. So what we'll do is we will pick back up here. Okay, so we're going to redo this piece. All right, thanks guys. Okay, so this is the remainder of lesson 3.2. We left off on step 3 of creating the table for my polynomial function 2x cubed plus x squared minus 8x minus 4. Okay, so we're going to finish this up. Step 1, we determined the end behavior for the polynomial function. Step 2, we found the zeros. Step 3, we broke it up into intervals, and we were in the process of creating our chart in order to give us a little bit more information on how to graph this. So we found the test values and the function values, and now we want to talk about the signs, okay? So the signs come from the value of the function value. So this piece here. Okay, that's where these signs come from. So -25 means we're negative, then positive, then negative, then positive. Okay, so what that means is the function is below the x-axis, above, below, and above. Okay, so that gives us a little bit more information when we want to go to graph it. Okay, so step 4 is to determine the y-intercept, and we do that by finding f of 0. Okay, so f of 0 equals 2 times 0 cubed plus 0 squared minus 8 times 0 minus 4. And that gives us a value of -4. So our y-intercept is the point 0, -4. Okay? So what we've done is we have pulled together a whole bunch of points, right? We have our y-intercept. We have our zeros. We have, let's see here, do we have any others? We have our test values. And that should be enough information to give us a general idea for this graph. Okay, so what we're going to do is we're going to put in our graph. Okay.
She goes out for a story. She goes out for a story. She's stalled by the neighbor's stupid gibber.
Okay, so this lesson is for Mrs. Cucci's College Now Pre-Calculus class. You should be on... Sorry about that, guys. Not 100% sure as to where that came from. Sorry about that. Okay, so now what we're going to do is we're going to put in our important points. So we've got the point 0, -4. We've got the point -2, 0, 2, 0, and -1/2, 0. This is not a point. Sorry about that. Oh, no. That's okay.
She was crossing the street. I forgot to look both ways. That's a good one. Right when she put her foot.
0, -4 should be here.
A semi-truck came out of nowhere. A Mack truck.
Okay. We have -325, which is going to be very, very low. I don't think we need to go that low on this axis. Okay, we've got -1, 3. We have 1, -9. And 335, which we're probably not going to use. Okay, so we know based on the information that we've already gathered that our end behavior is going to look something like this. So that means from this end, I'm going to be going down. Okay. We know that we are below the x-axis from -2 to -infinity, so we're good here. We're above the x-axis from -2 to +1/2, so we're going to be here. Okay. Then we're below the x-axis from -1/2 to 2. Okay. So it looks like we're probably going to do this. And then again, we're above the x-axis. So that gave us enough information to sketch out that graph pretty well. And again, we want to make sure we label. And we have our function. Okay, so all of that information that we need to gather. Okay, we're going to try another one of these. Okay, so we're going to continue through with our steps here, and we're going to use all of the things that we already learned and how we can graph this without using the aid of our calculator. So, step 1, as usual, is to use that leading term test. So, step 1, what we're going to do is we're going to look and we say, all right, our leading term is x to the 4th. Okay? The degree is 4, so it's even, and the coefficient is 1, which is positive. Okay, so we've got even and positive. So that tells me my end behavior as x approaches infinity is going to go up. As x approaches -infinity, it's also going to go up. So we're looking at something that is going to go up in either direction. Okay. Step 2, we're going to go through and we're going to find the zeros. So g of 0, or g of x equals 0. So this was nice for us. It gave it to us already nicely factored. So what we can do is we can use that already factored form to solve for the zeros. Okay, so we get x plus 1 equals 0, x minus 2 equals 0, and because it's squared, we write that twice, and x minus 4 equals 0. So we get x equals -1, 2, and the 2 occurs twice. We don't need to write that multiplicity. I'll just know that it does have a multiplicity of 2 and 4. Okay, so those are going to be our x-intercepts, -1, 0, 2, 0, and 4, 0. Alright, so what that does for us is it divides our intervals for us, right? That allows us to make intervals. So the intervals that we're going to be looking at are going to be those from -infinity to -1, -1 to 2, 2 to 4, and then 4 to infinity. Okay? So from our intervals we make our chart. Alright. we've got a couple of things that this chart's going to help us to find. Remember, first we need our test value, which from our test value gives us our function value. We find the sine, that's the sine of g of x, and then the location of where it is, above or below that x-axis. So we want to pick somewhat easy test values. So from -1, or negative infinity to -1, let's pick something just so you can see what it would look like if it wasn't pretty. -1.25. Okay. If I plug that in, I get about 13.9, and the sign for that's positive. The location would then mean that if we're going back 1.25 up 13.9, we're going to be above that x-axis. The value between -1 and 2 would be 1, which would give us -6, which of course is negative. So we're going to be below the x-axis. 2, 4, let's try 3. 3 is going to give us a value of -4, which is negative, and we're still below. 4.25, which is about 6.6. That's positive, so we're going to be dealing with above. Okay? So it gave us a whole bunch of information that we can use. Now, it's nice to draw it on a number line just so you can start to see, and you're going to use this quite a bit in calculus, so you should get pretty comfortable as to how this would be written. So that's why we're doing it. Okay, so we have some values that we were using. We know we were using -1, and we were using 2, and we were using 4. So we want to pick those values around it. So we chose that from our interval because we were from -infinity to -1. Above that x-axis is going to be positive. And then these two were negative, and this one was positive. Okay? So that's going to help us to understand how this graph is going to be positioned. Okay, so what we're going to do from there is our 4. And that is to determine that y-intercept. And we know we find the y-intercept by plugging 0 in for x. We're finding g of 0. So g of 0 equals 0 to the 4th minus 7 times 0 cubed plus 12 times 0 squared minus 16. That gives us a value of -16. Okay, so our y-intercept is 0, -16. All right. So essentially what that's done for us is it's given us a whole bunch of points that we can use, right? So we're going to gather those. We know we have 0, -16. We had our x-intercepts at -1, 0, 2, 0. I don't know why things keep disappearing on me. And 4, 0. Okay, those were our x-intercepts. And then we had some test points that we were able to find right here. So -1.25, 13.9, 1, -6, 3, -4, and 4.25, 6.6. Okay, so we have our y-intercept, our x-intercepts, and then some test points that we were able to determine. Okay, from that we should be able to graph this function. So I had a graph, put it all the way down here for some strange reason. Let's see if I can move it. Okay. so we're going to use this graph. Okay, so the first thing I need to do is I need to put on my axes. We're going to go through and plot our points. So we have 0, negative 16. Doesn't look like I have enough. So what I'm going to do is I'm going to erase my x-axis. I'm just going to adjust it. I want it to be up higher. Let's make it about here. Oops. Okay. So 0, negative 16. Oh, I'm one off. Goodness gracious. Let's try this again. Okay. We also have negative 1, 0. This is one of my zeros. 2, 0. 4, 0. Negative 1.25, so negative 1 1/4, 13.9, which isn't a pretty easy one to graph, so we're going to kind of hold off on that one for now. 1, negative 6. 3, negative 4. Okay, so from that we're going to see if we can piece together a graph. Now, we had some intervals. We said that from negative infinity to negative 1, right? Negative infinity to negative 1, I was above my x-axis. So this describes my end behavior, right? This is going to be going up to infinity. Okay? From there, I was below. Okay? And then from there again, I was also below. So I'm going up because that's my next point, but I'm going to go back down and then come back up. Okay, so I'm below, but I have to follow my points. And then from 4 to infinity, I was again above. So from my intervals here, I was above from here to here. Then I was below, and then again I was above. Okay, so it should follow that, which in this case it does. Okay, so that's how I was able to graph this, pulling out all my information, and of course I do need to label it. G of x equals 4x to the 4th minus 7x cubed plus 4x minus 16. Okay? So again, you have to know how to do these by hand, and you do need to find all of that information in order to do it. Okay, so next thing I want to talk about is that intermediate value theorem. Okay, so let's go back here. The intermediate value theorem for any polynomial p of x with real coefficients, we're going to suppose that a doesn't equal b. So p of a and p of b are opposite signs. When the function has a real zero between a and b. So the intermediate value theorem cannot be used to determine whether there is a real zero between a and b, but in cases where a and b have the same sign. So if p of a and p of b have different signs, we can assume that there's a solution between them. If they have the same sign, we can't assume that there is a solution between them. We're going to see what that looks like. Okay, so using the intermediate value theorem, determine if possible whether the function has a real zero between a and b. Okay, so here's what we do. I'm going to go back here. We have my original function f of x equals x cubed plus x squared minus 6x. In order to tell if there's the possibility of a solution between them, or a real zero between them, we're going to find f of A and f of B. Okay? So f of A, we know that A is -4. So f of -4 equals -4 cubed plus -4 squared minus 6 times -4. So f of -4 equals -24. Okay? So that's the first part. The next thing we need to do is we need to determine f of -2. Okay? So we do it the same way. -2 cubed plus -2 squared minus 6 times -2. We get f of -2 to equal 8. Alright? So because f of -4 is negative and f of -2 is positive, the intermediate value theorem states that there is a solution somewhere between -4, somewhere between -4 and -2. Okay, so there's a solution somewhere between -4 and -2. And how we would prove that is we would go and we would graph that to be sure. Okay, so here's my function. I'm going to insert a graph page. Okay. X cubed plus x squared minus 6x. When we look at the graph, there is indeed a solution between -4 and -3. And in this case, it looks like it's right on it. Or -4 and -2, I'm sorry about that. Okay, so there is indeed a solution between that. So we can justify it by looking at the graph. Okay. Okay. So let's try another one. Using the intermediate value theorem, determine if there's a real zero between A and B. Here's our function. We've got our values of A and B. A is -1, B is 3. Okay. We're using the same function, so we're going to find f of -1. -1 cubed is -1 plus -1 squared, which is +1, so this is going to equal 6. And f of 3, which is going to give us a value of 9 plus 9, which is 18. Oh, I'm sorry, 27 plus 9 minus 18, which is going to give us 18. Okay, now the sign here is positive, the sign here is also positive. So we're going to say that because there is no sign change, the intermediate value theorem does not allow us to determine whether or not there's a zero. So we can't say that there's not a zero, but we can say that the intermediate value theorem doesn't allow us to determine if there is or not. So that you would have to verify graphically as well. Okay. So, how much time do we have left? Oop, I am over again. Okay, so we'll continue practicing these. I want you to try the last two on your own and come prepared with any questions that you might have. Sorry guys, I didn't realize I was over. Alright, we'll see you tomorrow.